Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we're exploring a critical aspect of workplace safety, ensuring accurate radiation monitoring. We'll highlight a key research study from Morocco titled Dosimetrology, TLD, OSL, Dose Accuracy and Energy Response Performance. The study was a collaborative effort led by Dr. Omaima Essaad Belhaj and her colleagues, bringing together experts from the University Abdelmalek Essaadi, Ibn Tufayl University, and the National Center for Radiation Protection in Morocco to tackle this vital issue. This research compares two key passive dosimetry systems, wearable devices that silently record exposure for radiation workers. The study evaluates TLDs or Thermoluminescent Dosimeters against OSLs, which are optically stimulated luminescence dosimeters. Both systems are essential for monitoring individual radiation doses for workers exposed to X-rays and gamma radiation. They are crucial safety tools in hospitals, nuclear facilities, and medical imaging centers where precise monitoring protects long-term health. To compare these technologies, the study focused on three key performance aspects. First is dose accuracy, the most fundamental job of a dosimeter. It measures how close the reading is to the actual radiation dose delivered. Second, energy response, testing performance across different radiation energies. And third, the coefficient of variation. This measures consistency, telling us if we can trust the results to be reliable and repeatable every single time. So, what did the results show? Importantly, both TLD and OSL technologies successfully complied with the stringent ICRP recommendations and IEC 62387 international standards, meeting a critical baseline for safety and quality. However, a closer look revealed that OSL technology consistently performed better. It demonstrated higher sensitivity and superior accuracy, especially at the low doses healthcare workers are frequently exposed to, providing more stable results. TLD, while acceptable for deep dose measurements, was found to be less accurate for skin dose at certain exposure levels. This is a crucial distinction when monitoring for potential skin injuries. In Morocco, the National Center for Radiation Protection supervises workers' radiation doses monthly. This diligent monitoring is critical because excessive exposure is a silent threat. It can damage DNA, leading to cellular mutations that increase long-term cancer risk and can harm sensitive internal organs. By adopting more advanced systems like OSL, Morocco ensures stronger protection for its workforce. This modern technology offers greater sensitivity and accuracy, providing a more reliable safety net for health professionals and industrial workers regularly exposed to ionizing radiation. The findings align with the IEA safety standards and the ALARA principle. This philosophy means taking every reasonable step to keep radiation exposure as low as reasonably achievable, a cornerstone of modern radiation protection. This research is not only vital for Morocco but also for many countries worldwide. Radiation safety is essential in medicine for diagnostics and therapy, in nuclear technology, and in countless industrial applications that power our modern world. In conclusion, this study demonstrates how scientific innovation in radiation dosimetry can directly enhance workplace safety and ensure compliance with global nuclear safety regulations. Thank you for watching For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel. Today we present an outstanding research contribution from Morocco in the field of radiation protection and nuclear safety. The research is titled Dosimetrology, TLD OSL Dose Accuracy and Energy Response Performance. Dr. Omaima Essaad Belhaj, Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. Professor Hamid Boukal, Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. Professor El Majoub Chakir, LPMS, Faculty of Sciences, Ibn Tofel University, Kenitra, Morocco. PhD student Marieme Bellasawiya, LPMS, Faculty of Sciences, Ibn Tofel University, Kenitra, Morocco. Professor Siham Belhaj, ENA, Marrakesh, Morocco. Mr. Yunus Sadek, Head of Laboratory, LPMS, Faculty of Sciences, Ibn Tofel University, Kenitra, Morocco. Dr. Mohammed Tazi, SSDL, National Center of Radiation Protection, Ministry of Health, Sale, Morocco. Dr. Tahar El Kouki, National Center for Energy, Science and Nuclear Technology, Morocco. PhD student Mariam Hadawachi, Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. PhD student Kaula Lazouzi, Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. Published in Nuclear Engineering and Technology, Volume 55, Issue 2, February 2023. The paper underwent rigorous peer review from March 2022 to February 2023. This work evaluates two widely used passive radiation dosimeters, Thermoluminescent Dosimeters or TLDs, and Optically Stimulated Luminescence Dosimeters, known as OSLs. Both are essential tools for radiation workers' safety, monitoring cumulative radiation doses in compliance with international safety standards. This valuable study was carried out by a distinguished team of 10 Moroccan researchers from leading institutions including University Abdelmalek Essaadi, Ibn Tofel University, and the National Center of Radiation Protection. Led by Dr. Omaima Essaad Belhaj and Professor Hamid Boukal from the Radiations and Nuclear Systems Laboratory, along with Professor El Majoub Chakir and the dedicated research team. The team conducted comprehensive testing comparing dose measurement accuracy, energy response, and statistical variation between TLD and OSL systems. The findings confirm that both systems met international IEC 62387 standard requirements for dose accuracy. However, OSL dosimeters showed superior performance. OSL dosimeters demonstrated higher sensitivity, better energy response, and lower statistical dispersion compared to TLDs, making them especially suitable for precise occupational radiation monitoring. These results align with international radiation protection guidelines, ensuring worker safety in environments where ionizing radiation is present, both in Morocco and worldwide. This research represents a valuable step forward in radiation safety monitoring. We extend sincere congratulations to the entire research team. Share your thoughts on this research in the comments below, and stay tuned for more scientific insights here on 4 Science Salah Lotfy channel.
In fields from medical imaging to nuclear power, protecting professionals from the invisible hazard of ionizing radiation is paramount. This protection begins with precise measurement, the domain of passive dosimetry, tracking cumulative radiation exposure with powerless devices. This pivotal Moroccan study evaluates the two leading technologies in this field. The first is the Thermoluminescent Dosimeter, or TLD. TLDs contain crystals that trap energy from radiation. When heated in a lab, this energy is released as light and the light's intensity reveals the dose. The second technology is Optically Stimulated Luminescence, or OSL. OSL dosimeters also trap energy, but a laser is used to stimulate the sensitive material, causing it to release light for measurement. The study's objective was to compare these systems against stringent international standards. Researchers focused on two key metrics: dose accuracy and energy response. Dose accuracy ensures the reading matches the actual dose, preventing unsafe underestimations or unnecessary work restrictions. Energy response ensures reliability across different radiation energies, crucial for workers near various sources. To do this, dosimeters were irradiated under precisely controlled conditions at a secondary standard dosimetry laboratory, simulating real-world performance. The findings were illuminating. The research confirmed that both TLD and OSL systems in Morocco meet demanding international requirements, a testament to the country's high safety standards. However, the investigation revealed a critical advantage for OSL dosimeters. They demonstrated significantly higher sensitivity and superior accuracy, particularly at the low dose levels typical for occupational exposure. This is vital for tracking small, cumulative doses over a career. Furthermore, OSL technology offers the invaluable benefit of being rereadable. The reading process doesn't erase the signal, allowing for dose verification and creating a permanent archival record, a feature TLDs lack. This research has profound implications, strengthening Morocco's radiation safety infrastructure. As the nation expands its use of nuclear technologies in medicine, industry, and research, having robust empirical data to guide the selection of dosimetry systems is essential. It empowers regulatory bodies and healthcare institutions to make the most informed choices, ensuring the highest level of protection for their personnel and building national expertise in radiation protection metrology. Ultimately, these advancements enhance safety for the individual worker. They reinforce the cornerstone philosophy of radiation protection, the ALARA principle, which stands for keeping radiation exposure as low as reasonably achievable. ALARA isn't just about meeting legal limits, it's a commitment to continuous optimization. The superior low-dose accuracy of OSL dosimeters provides the high-quality data needed to make ALARA a practical reality. It allows safety officers to detect subtle exposure trends and work with staff to minimize their dose. This proactive approach, fueled by precise measurement, is the future of occupational health. Thank you for watching for Science Salah Lotfy channel, where we bring global scientific research closer to everyone. Welcome to For Science Salah Lotfy channel. Today we explore an important study from Morocco that focuses on radiation protection for workers exposed to ionizing radiation. The research is titled Dose Metrology, TLD OSL Dose Accuracy and Energy Response Performance. It was conducted by Dr. Omaima Essaad Belhaj and her colleagues at the University Abdelmalek Essaadi and the National Center for Radiation Protection of Morocco. Radiation workers in medical, nuclear, and industrial fields are exposed daily to ionizing radiation. To monitor and protect them, two types of passive dosimeters are commonly used. TLD, Thermoluminescent Dosimeters, OSL, Optically Stimulated Luminescence Dosimeters. This study compares their performance in three key areas: dose accuracy, how close the measured dose is to the actual delivered dose; energy response, how reliably the dosimeter measures radiation at different photon energies; coefficient of variation, the consistency of the readings and their statistical stability. The evaluation was based on international safety standards, including the recommendations of the International Commission on Radiological Protection, ICRP, and the IEC 62387 standard for radiation protection instrumentation. The growing use of ionizing radiation in healthcare, nuclear science, and industry creates increasing challenges for safety. More strict regulatory limits are being enforced, along with higher demands for quality control in dosimetry. If radiation doses are not carefully monitored, workers may suffer serious health consequences such as DNA damage, organ failure. Increased cancer risk. This is why passive dosimeters play a vital role. They are worn by each individual working in radiation areas, and their cumulative monthly doses are read by regulatory authorities. In Morocco, this responsibility is carried out by the National Center for Radiation Protection, CNRP, under the regulatory framework of Law Num 142/12 on Nuclear and Radiological Safety and Security, issued in 2014, Decree Num 297/30 on protection against ionizing radiation. Only two types of dosimeters are authorized for use in Morocco: TLD, which uses lithium fluoride crystals, LIFE MGTI, to simulate tissue absorption of X-rays and gamma rays; OSL, which uses aluminum oxide crystals, Al2O3C, that store radiation energy and release it as light when stimulated. The research team compared OSL and TLD dosimeters in terms of HP 10, representing deep tissue dose, and HP 0.07, representing skin dose. Here are the key findings. Dose accuracy. Both OSL and TLD gave results within ICRP acceptance limits. Energy response. OSL outperformed TLD, providing measurements closer to the ideal case across different photon energies. Coefficient of variation. OSL satisfied the ISO 62387 requirements for both HP 10 and HP 0.07, while TLD met the requirements only for HP 0.07. In short, OSL technology demonstrated superior precision, sensitivity, and stability, especially for low-dose exposures. For Moroccan radiation workers in hospitals, nuclear centers, and laboratories, these findings are critical. Accurate dosimetry ensures compliance with safety limits and reduces long-term health risks. Globally, the results highlight the importance of adopting OSL dosimetry as it aligns with the IEEA safety standards and the ALARA principle, keeping radiation exposure as low as reasonably achievable. By using OSL systems, countries can enhance occupational health protection and strengthen nuclear safety practices in line with international regulations. This Moroccan study confirms that while both dosimetry systems are acceptable, OSL is the more reliable choice for protecting workers from ionizing radiation exposure. It is a significant contribution not only for Morocco, but also for all countries where radiation is part of daily professional life. Thank you for joining us on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. We live in a world permeated by invisible forces, and among the most significant is ionizing radiation. While it's a natural part of our environment and a vital tool in medicine, industry, and energy production, its potential for harm necessitates meticulous monitoring and control. The cornerstone of this safety is radiation protection, a field dedicated to safeguarding individuals and the environment from the adverse effects of radiation exposure. At the heart of this discipline lies the science of dosimetry, the precise measurement of absorbed radiation dose. Accurate dosimetry is not just a scientific pursuit, it is a legal and ethical obligation to protect the health of thousands of occupational workers every single day. In today's episode, we continue our exploration of cutting-edge radiation protection research conducted in Morocco. We'll be taking a deep dive into a comprehensive study that performs a critical performance evaluation of two leading passive dosimetry technologies, Thermoluminescent Dosimeters, or TLDs, and Optically Stimulated Luminescence, or OSL dosimeters. This comparative analysis is crucial for ensuring that the tools we rely on for safety are as accurate and reliable as possible. The first device we will examine in detail is the OSL dosimeter, a state-of-the-art technology manufactured by Landauer, a global leader in radiation science. The sensitive heart of this dosimeter consists of 4 identical elements. These are not just simple pieces of material, they are precision-engineered discs of carbon-doped aluminum oxide, or Al2O3C. This specific crystalline compound is chosen for its remarkable sensitivity to radiation and its ability to retain a record of exposure over long periods. Each tiny element measures just 5 millimeters in diameter and a mere 0.3 millimeters in thickness, a compact design that belies its powerful capabilities. The inclusion of 4 separate elements provides redundancy and allows for sophisticated dose assessment. These sensitive elements are securely placed inside a specially designed holder, which is far more than a simple plastic case. The holder is an integral part of the measurement system, incorporating 4 distinct types of filters, each positioned over one of the aluminum oxide elements. The first is a polyethylene window, essentially an open window, designed to measure shallow dose from beta particles and low-energy photons, critical for assessing skin exposure. Next is a plastic filter, which helps determine the dose to the lens of the eye. The third filter is made of aluminum, which effectively blocks beta radiation and allows for the assessment of photon energy. Finally, a copper filter provides the greatest attenuation, enabling the system to discriminate higher energy photons and accurately calculate the deep dose, which corresponds to the effective dose to the whole body. By analyzing the different signal levels from beneath these 4 filters, a sophisticated algorithm can determine not only the dose but also the type and energy of the radiation the wearer was exposed to. The physics behind OSL technology is both elegant and powerful. When ionizing radiation, such as X-rays or gamma rays, passes through the aluminum oxide crystal, it transfers energy to the atoms. This energy excites electrons, elevating them to a higher energy level. Some of these electrons become lodged in imperfections or traps within the crystal's lattice structure. They remain in this trapped, metastable state, creating a latent record of the radiation exposure. The magic happens during the readout process. The dosimeter is exposed to a very specific wavelength of light, typically from a green light-emitting diode or LED. This light provides the precise amount of energy needed to free the trapped electrons. As these electrons return to their stable ground state, they release their stored energy in the form of a faint flash of blue light. The intensity of this emitted light is measured by a highly sensitive photomultiplier tube, and it is directly proportional to the initial radiation dose absorbed by the crystal. To analyze the dosimeters, the researchers in this study utilized an automated in-light reader system. This integrated setup is essential for any large-scale dosimetry service, ensuring high throughput, consistency, and minimal human error. The system comprises 3 key parts: the optical reader itself, which houses the stimulation LEDs and the light detection system, a connected external PC that powers the operation, and the dedicated Landauer software. This specialized software is the brain of the operation. It not only controls the reader's mechanical functions but also records the raw light output, applies crucial calibration factors, and executes the complex dose calculation algorithms to generate a final legally defensible dose report. Moving on to our second system, we examine the Thermoluminescent Dosimeter, or TLD, specifically the Harshaw model. TLDs are a cornerstone of personnel dosimetry, valued for their high sensitivity and reusability. At its heart are two small lithium fluoride crystals. This material is chosen because it is nearly tissue equivalent, absorbing radiation like human tissue. To function, the crystals are doped with titanium and magnesium, creating specific imperfections within the crystal structure that are key to recording radiation exposure. The crystals are housed within a holder that is much more than simple casing. It incorporates a series of filters, including tissue-equivalent plastic, PTFE, Mylar, and Teflon. Each filter has a different density, allowing it to block or permit different types and energies of radiation. For instance, a thin Mylar window allows beta particles to reach one crystal to measure skin dose, while thicker filters allow higher energy photons through to the second. By comparing readings, we can determine shallow, eye, and deep dose equivalents. So, how does this work on a subatomic level? When ionizing radiation passes through the lithium fluoride crystal, it excites electrons out of their stable ground state. Normally they would immediately return, but the magnesium and titanium dopants create electron traps, metastable energy levels. Many excited electrons fall into these traps and become stuck. The number of trapped electrons is directly proportional to the radiation dose absorbed. To retrieve this stored information, the TLD is placed into an automated reader. Inside, a precisely controlled heating cycle gives the trapped electrons the energy to escape. As they return to their ground state, they release their excess energy as photons, tiny flashes of light. This phenomenon is called thermoluminescence, thermo for heat and luminescence for light. A sensitive photomultiplier tube inside the reader detects this emitted light, and the data is plotted as a glow curve, showing light intensity versus temperature. The curve displays several distinct peaks, each corresponding to a different set of electron traps. Deeper traps require higher temperatures for release. By analyzing the area under these peaks, a computer algorithm calculates the precise radiation dose with exceptional accuracy, as the total light output is directly proportional to the dose received. For a dosimeter's reading to be meaningful, it must be impeccably accurate. This requires calibration against internationally recognized standards. To validate our systems, experiments were conducted at a secondary dosimetry calibration laboratory, or SSDL, in Rabat, Morocco. This laboratory is a key member of the international network established by the World Health Organization and the IEA. This network ensures that radiation measurements are consistent and comparable worldwide, which is critical for radiation protection, medical treatments, and regulatory compliance. Inside the SSDL, the dosimeters were exposed to precisely known quantities of radiation using two distinct systems. The first was an X-ray irradiator, Model X8320. This system generates X-rays across a broad energy spectrum from 15 to 320 kilovolt peak, crucial for testing response to lower energy radiation found in diagnostic radiology. The second was a gamma irradiator with sealed sources of cesium-137 and cobalt-60. These isotopes emit high-energy gamma rays, characteristic of environments in nuclear medicine and industrial radiography. Using both ensures a comprehensive evaluation across the full spectrum of energies. Our testing methodology begins with a foundational measurement, the air Kerma rate. Kerma stands for kinetic energy released per unit mass, quantifying the energy transferred from radiation to a unit mass of air. It's the starting point for all dose calculations. We use the formula K-air equals Ri times Nk times KTP. Ri is the raw charge rate from our detector. We refine this with Nk, the chamber's official calibration factor, ensuring traceability to international standards. We also apply KTP, a factor that corrects for ambient temperature and pressure, since air density affects the measurement. This meticulous process ensures our baseline is exceptionally accurate. For this measurement, we use a PS50 ionization chamber and a PTW Unidos electrometer. The chamber collects ions created by radiation, and the electrometer precisely measures the resulting electrical current. However, a measurement in air isn't the final goal. We need to know the dose a person would receive. Therefore, we convert the air Kerma value into the personal dose equivalent, HP 10, for deep body dose and HP 0.07 for skin dose. This critical conversion follows the strict protocols of the ISO 4037 international standard, which provides the coefficients to translate a physical measurement into a biologically relevant dose. Next is the irradiation of the dosimeters. To ensure statistical robustness, we irradiate them in groups of 3 for each test point, allowing us to average the results and check for consistency. The dosimeters are placed on a water phantom, which simulates the absorption and scattering properties of human tissue, a crucial step for accurately measuring personal dose. The entire setup is positioned at a precise distance of 250 centimeters from the source to guarantee a uniform radiation field. To ensure performance in various real-world scenarios, we test against multiple radiation qualities, reference X-ray beams N60, N80, and N150, representing a range of energies, and a cesium-137 source for high-energy gamma radiation validation. Following irradiation, the dosimeters are not read immediately. They are stored in a controlled environment for 24 hours. This waiting period is for stabilization. Inside the dosimeter's crystal, radiation traps electrons, and the number of trapped electrons corresponds to the dose. However, some electrons are in unstable traps and can leak out over time, a process called fading. By waiting 24 hours, we allow these unstable signals to disappear, ensuring our final reading is based only on the stable, dose-proportional signal. This step is vital for preventing an overestimation and guaranteeing an accurate result. Finally, we analyze the data, beginning with accuracy. Accuracy tells us how close our measured dose is to the true delivered dose. We calculate this by taking the ratio of the measured dose to the delivered dose. An ideal result is a ratio of 1. We then plot these ratios on the trumpet curve graph as defined by the International Commission on Radiological Protection, ICRP. The acceptance boundaries are wider at low doses, where uncertainty is higher, and tighter at high doses. For a dosimeter to pass, its performance ratio must fall within these limits. Next, we assess precision, which measures the consistency of our dosimeters. Using the readings from our groups of 3, we calculate the coefficient of variation, or CoV. This is the standard deviation of the group divided by its mean dose expressed as a percentage. A low CoV indicates high precision. We adhere to the limits set by the IEC 62387 standard, which allows a CoV of up to 15% for low doses but demands a much tighter CoV of no more than 5% for doses above 1.1 millisieverts. Meeting these dual criteria for both accuracy and precision is the ultimate proof of a reliable dosimetry system. Through this rigorous methodology using advanced irradiation facilities, carefully designed filters, and strict international standards, the Moroccan research team ensured a reliable comparison between OSL and TLD dosimeters.
The next part of the study presents the results and discussion, where we will see how each dosimeter performed under these experimental conditions. Stay tuned for more insights on For Science Salah Lotfy channel.
Welcome back to For Science Salah Lotfy channel. In this episode, we continue our journey into the Moroccan research study comparing TLD and OSL dosimeters for radiation monitoring. After discussing the experimental setup and methodology, we now move into the results and discussion. To begin, the researchers evaluated the coefficient of variation. This is a crucial test that measures the statistical fluctuations of dose readings, essentially quantifying the dosimeter's precision or repeatability. A low coefficient of variation indicates that the dosimeters provide highly consistent and therefore reliable results. The performance benchmarks are dictated by the IEC 62387 international standard, which sets the official performance requirements for dosimetry systems. According to this standard, the limits are, for HP 10, the deep dose equivalent, at very low doses, less than 0.1 millisieverts, a maximum variation of 15% is allowed, acknowledging challenges near the detection limit. Between 0.1 and 1.1 millisieverts, the variation can be up to 16%, but must decrease as the dose increases. Above 1.1 millisieverts, the maximum variation is a tight 5%. For HP 0.07, the skin dose equivalent, for doses less than 1 millisievert, the maximum variation is 15%. In the range of 1 to 11 millisieverts, a gradually reduced variation is required, and for doses above 11 millisieverts, the maximum variation is also capped at 5%, reflecting specific protection limits for skin. To test against these thresholds, groups of dosimeters were irradiated at 4 different dose levels, chosen to cover the standard's performance ranges. For HP 10, the test levels were 0.25, 1.5, 3, and 6 millisieverts. For HP 0.07, the corresponding levels were 0.26, 1.55, 3.4, and 6.25 millisieverts. For each group, the standard deviation of the readings was divided by the mean dose to calculate the coefficient of variation. This provides a standardized measure of relative variability. This test was carried out together with the nonlinearity response test to build a comprehensive performance profile. The nonlinearity test evaluates whether the dosimeters maintain proportionality between delivered and measured doses. According to IEC 62387, the variation must not exceed plus 9% to plus 11%. The researchers found that both OSL and TLD generally complied with this standard, except for one case at 6 MSV where the TLD slightly exceeded the acceptable range. Figures 7 and 8 in the study illustrate the R10 and R0.07 values, representing the ratio of measured to delivered doses. The results are very significant. All 24 data points from both OSL and TLD were within the trumpet-shaped acceptance graph set by the ICRP. However, there was a clear difference. OSL results were tightly clustered, reflecting high sensitivity and precision. TLD results were more dispersed, particularly at doses below 1 MSV. This difference is explained by the lower detection limits. TLD, 10 mrem, OSL, 1 mrem. The lower detection limit of OSL allows it to capture small doses more reliably, which is essential for occupational exposure monitoring and meeting the ALERA principle, as low as reasonably achievable. Another major focus was the energy dependence of both dosimeters. This is a critical characteristic, as an ideal dosimeter should measure dose accurately, regardless of photon energy. Any significant variation can lead to incorrect readings. The goal is a response that is energy independent, reporting the true dose value across a wide spectrum of energies. To evaluate this, researchers used a range of photon energies. They employed standardized X-ray beam qualities, N60, N80, and N150, with mean energies of 48, 65, and 118 keV. For a high-energy reference, they used the well-defined 662 keV gamma radiation from a cesium-137 source. The results confirmed that OSL measurements were consistently closer to the ideal case. While both systems satisfied the international standard IEC 62387, the TLD's response for deep dose, or HP10, frequently approached the lower acceptance limits. This indicates a smaller margin for error, especially at higher energies. The quantitative data makes this distinction clear. For deep dose HP10, the OSL's maximum response variation was only 14.6% versus 21.5% for the TLD, with an average deviation of just 5.0% compared to the TLD's 13.6%. The pattern held for shallow dose HP 0.07. OSL again outperformed TLD, showing a maximum variation of 16.7% and an average deviation of 7.3%, compared to TLD's 23.9% and 10.4% respectively. This proves that OSL is consistently closer to the ideal energy response. The primary reason for the TLD's poorer performance is a phenomenon known as supralinearity. This effect, inherent to the TLD's lithium fluoride crystals, causes the material to produce a disproportionately high signal at lower photon energies, inflating the measured dose. In contrast, the aluminum oxide in OSL dosimeters is not susceptible to this, allowing it to maintain a more linear and stable response across the entire energy range. Figures 11 and 12 in the study show the coefficient of variation results. For OSL, both HP10 and HP 0.07 remained within IEC limits across all doses. For TLD, HP10 was acceptable, but HP 0.07 did not meet the standard for doses above 1 MSV. This demonstrates that OSL not only provides higher sensitivity, but also greater statistical reliability. Figures 13 and 14 illustrate the non-linearity of response for both systems. Both OSL and TLD generally fell within the plus 9% to plus 11% range set by IEC 62387. Only one exception was noted at 6 MSV for TLD, where it exceeded the tolerance. This reinforces the finding that OSL performs more consistently across the entire tested dose range. After rigorous testing, the study's conclusions provide a definitive verdict on these two technologies. Let's break down the key findings that emerged from the data. First, OSL dosimeters show significantly less energy dependence. This is crucial, as it ensures accuracy across the varied spectrum of radiation energies found in the workplace. This superior accuracy applies to both deep dose, HP 10, for internal organs, and skin dose, HP 0.07, guaranteeing more comprehensive and reliable protection. Second, while both systems met the baseline international accuracy standards, OSL technology consistently outperformed TLD. This wasn't just about passing the test, it was about demonstrating a higher margin of safety and reliability in every measurement. Third, a critical failure point for TLD emerged when testing the coefficient of variation, a measure of precision. The TLD system did not meet the stringent IEC 62387 requirements at higher skin doses, indicating potential unreliability in certain exposure scenarios. In stark contrast, the OSL system satisfied all precision requirements, proving its robustness under all conditions. Fourth, in terms of linearity, the proportionality of the reading to the actual dose, both systems were acceptable. Yet again, OSL demonstrated greater stability across the entire dose range. This stability ensures that measurements are trustworthy, from low background levels to more significant exposures. The practical implications stem from the core physics. OSL uses a controlled beam of light, a non-destructive process that allows the dose to be reread multiple times for verification or archival, a major advantage for quality assurance. TLD, by contrast, uses heat, which aggressively releases all stored energy in a single irreversible reading. This makes the measurement final with no chance for reanalysis, permanently losing the data if an error occurs. This Moroccan study from the National Center for Radiation Protection is more than just a comparison, it's a robust validation. It confirms OSL systems as a superior and highly reliable tool that meets the demanding IEC 62387 standards. The results showcase Morocco's high-quality radiation metrology capabilities and contribute vital data to the global scientific community. This work reinforces IAEA safety principles and helps improve health protection for radiation workers worldwide. Thank you for watching for Science Salah Lotfy channel. Our mission is to make complex science accessible. Subscribe and stay tuned for more explorations that transform research into knowledge for everyone, contributing to a safer, more informed world.
Welcome to For Science Salah Lotfy channel. Today, we highlight a significant Moroccan contribution in the field of radiation protection and nuclear safety. This work brings together experts from several leading institutions, each of whom played a vital role in advancing research on radiation dosimetry. Let us first recognize the distinguished research team. Dr. Omaima Essaad Belhaj from the Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. Professor Hamid Boukal, also from the Radiations and Nuclear Systems Laboratory, Faculty of Sciences, University Abdelmalek Essaadi, Tetouan, Morocco. Professor El Majoub Chakir from LPMS, Faculty of Sciences, Ibn Tufayl University, Kenitra, Morocco. PhD student Mariam Abel Asawiya from LPMS, Faculty of Sciences, Ibn Tufayl University, Kenitra, Morocco. Professor Siham Belhaj from ENA, Marrakesh, Morocco. Mr. Yunus Sadek, Head of Laboratory from LPMS, Faculty of Sciences, Ibn Tufayl University, Kenitra, Morocco, also affiliated with the SSDL, National Center of Radiation Protection, Ministry of Health, Sale, Morocco. Dr. Mohammed Tazi from the SSDL, National Center of Radiation Protection, Ministry of Health, Sale, Morocco. Dr. Tahar El-Kouki from the National Center for Energy Science and Nuclear Technology, Senetsen, Morocco. This collaborative research strengthens scientific knowledge in the field of radiation monitoring, providing insights that are crucial for protecting health and safety in nuclear and radiation environments. Before we close, I would like to extend my sincere appreciation, on behalf of myself, Professor Dr. Salah Lotfy, Professor at the Egyptian Atomic Energy Authority, to all the researchers for their outstanding work and contribution to science. And to our viewers, thank you for following For Science Salah Lotfy channel. We invite you to share your thoughts and comments on this important research in the section below the video. Your engagement helps us bring science closer to everyone.